Hola.
Hello.
Hello, hello.
Hola, hola.
Bueno, estamos esperando. ¿Ustedes tienen preguntas? Está abierto. ¿Sí, no? ¿Todo bien?
Yo quería preguntar algo sobre la tarea, pero a lo mejor quizás cuando haya más gente va a ser más útil.
Ah, claro. Sí, probablemente hay más que una persona que tiene lo mismo.
Así que quizás al final de la clase podría preguntar.
Recuerdo que alguien en el chat de WhatsApp del grupo notó que las reuniones del viernes, la hora de consultas calza con fronteras, con el Lastro PH.
Está como
Parece.
directamente después.
Ya, perfecto.
Pues, fronteras es 11:30 a 12 y directamente después mi oficina.
Correcto,
Pues,
verdad.
¿Cuándo puedo
¿Profe?
recargar?
Una consulta.
Sí.
El viernes debemos entregar la tarea, ¿cierto?
Disculpa, repite.
El viernes debemos entregar la tarea.
Sí, vienes a medianoche.
Ok, gracias.
Sí, y ya. Ahora puedes cambiar su nombre.
¿Por qué? Ok.
No sé por qué. Pero ya, tiene acceso para cambiar nombres ahora. Es una opción en seguridad para mí. Ok, entonces creo que tenemos todo. Entonces, ya. Bueno, no sé, ¿tú quieres preguntar su pregunta ahora o después?
Me dio la palabra, ¿cierto? Que se me cayó justo el internet.
Perdón.
¿Sí?
Sí.
En el problema 2, ¿está bien asumir que las estrellas reflejan luz también? ¿O no?
La estrella de neutrono.
Cualquiera de las dos, en verdad.
Sí. Sí, si tú quieres. Si tú quieres sumar o tener una asunción sobre el albedo, todo bien. Sí.
Ya.
Es un poco abierto en este sentido. Creo que vas a encontrar que la porción para reflexión no es tanto.
Sí me di cuenta.
Pero si quieres demostrarlo, está bien. Ok. Entonces, vamos a comenzar. ¿Ya?
Yo
Sure.
tengo otra pregunta sobre la tarea. Es que cuando calculamos el flujo que se refleja en el planeta, hay una fórmula, pero esta depende de una función, que es la función de fase, que depende como de los datos orbitales del sistema.
Sí.
Ya.
Y es entre 0 y 1.
Ya. Ya. Tengo que pensar más sobre eso, pero gracias.
Sí. Okay. Let's begin then. Let me find, I'll share my screen and see what we get. Okay, nothing there, something here. Okay, good. Okay, then. So I want to start with an example, just to put you guys in the mood. And so, we've been talking about the incident radiation or intensity that's emitted from something, and then it passes through some space, and that space may be, let's see, populated with gas, and then it arrives to the observer, right? And so let's think about things in terms of a very practical situation. So we have a solar-like star, right? So a G-type star, temperature 6,000 degree Kelvin on the surface, and it has an intensity of 10 to the minus 10 ergs per second per centimeter squared per steradian. And that light passes through 1 parsec of neutral gas, which is purely hydrogen at the moment. And this gas has a density of 1 atom per cubic centimeter. And we want to know what is the observed spectrum. And so how do you calculate that? What formula do you use?
The transfer radiation formula for absorption and emission.
So exactly. So we'll use something like this. We don't have any sources of emission, so it's just how this thing is absorbing the incident radiation, right? And so we have some ISM of hydrogen with some number density, and so in essence we can figure out how much of that is absorbing this, right? And I haven't really given you all of the tools to do that yet, but you can kind of get something together. So if we were going to think about this, so we have the optical depth, right? This is tau here, and that optical depth is merely the absorption coefficient times the path length. And we're going to go between 0 and L, where L is 1 parsec, right? And we also know that this thing can be expanded to be equal to sigma, which is the cross-section, and the number density. And this cross-section is the cross-section of hydrogen, right? And N is just the number of hydrogen, which we have here. And so we then can think about, okay, well, we have a classical hydrogen atom, right? Neutral hydrogen has a cross-section which is related to its size. And so the size of the radius of a hydrogen atom is something like 5 times 10 to the 9 centimeters. And so we can think of it as just a circle. And we can then calculate what the cross-section will be, the classical cross-section, right? And so we get some number which is something like that. And so if we just plug in what tau is and integrate over L here, so we're integrating 1 parsec, which is that in centimeters. Then we're integrating N, which is the density, and then the cross-section. And so it turns out tau is quite high, right? So what does that mean? You plug tau into here and take the exponent of minus 279, and that is a very, very small number. And so what that means is that when you multiply these together, the incident radiation, the radiation that we detect at the other end of this is very, very little, right? Most of that radiation has been absorbed or scattered or what have you by the hydrogen atoms, right? And then just a very classic approach to this problem, and we can probably do a little bit better with this. We can plug in, instead of this classic cross-section, we could plug in other processes, right, to do the other things depending on what the situation was. But this just gives you a very brief, very simple example of how you would use this in practice. Does it make sense? Any questions? Okay,
I have a question. What was A sub 0?
Where's A sub 0? Here, this is just the radius of the hydrogen atom.
Ah, okay.
right? This is just the Bohr radius. That's all.
Okay.
Okay,
Thank you.
good. This happens to be a very high density, right? This is like the density in H2 region. So typically the density in most of the ISM is orders of magnitude less than that. And of course that helps, because a few orders of magnitude, this now becomes close to 1 or less than 1. And so then it's fine. The radiation passes without much incident, right? Just to give you a feeling. Okay, so let's finish up chapter 1. And the last portion of this is taking the absorption coefficient and the emission coefficient and thinking about them in a little bit broader context. And so basically we can think about these absorption emission coefficients using what we call the Einstein coefficients, which is what we use for radiation, for line emission, typically. But you can actually expand this to more or less any situation. And so we can write Kirchhoff's laws for atoms in the language of Einstein coefficients, A and B. And so thinking about line emission, we'll come back to this much later in the semester. But just thinking about, we have a very simple system. So we have a 2-level system where we have the upper level and the lower level of an atom. And we have either the emission process where an electron drops from level 2 to level 1, and it sheds some excess energy in the form of a photon, right? And the opposite, a photon comes in, the electron absorbs it and is able to climb to a higher level. Right? So those are our two properties here. And so with this spontaneous emission, we have the electron at a higher level, it drops to a lower level, and it radiates a photon. The probability of this happening can be given by this Einstein A coefficient, which is just the probability of a transition per unit time for emission. So it's in per second. And likewise, we have the absorption. And for an absorption to occur, we need to have a photon come in. The photon will have an energy h nu 0. And this will, with the absorption of this, the photon will jump up to the level 2. Now here, there's no self-interaction of the radiation field. And so the probability of this happening should be proportional to the photon density of these photons with frequency mu naught. This isn't necessarily a delta function, but it has a little bit of a width. And so we can think about there's some probability that this photon, this electron will absorb a photon which is slightly less than the energy or slightly higher than the energy, slightly lower frequency, slightly higher frequency. And so it has some width, which looks like that. And photons in that range will allow the electron to move up. And so because this isn't a delta function, basically we have this line profile. And if we integrate it over all frequencies between 0 and infinity, we should get 1. That's sort of the normalized line profile function. And so then we can define an Einstein B coefficient, which is the probability of a transition upward, right, or the probability of an absorption. And this is going to be related to the line profile and the radiation field, which is denoted by delta J, right, which is the average energy density. And if we integrate this over all of frequencies, then we end up with this, the average energy density here. Okay, so that defines 2 of the processes. We also have stimulated emission. And so basically, as a result of Planck's law, we require something which is the opposite of absorption. And the absorption requires a photon. And so it requires an external photon field. And so there is this opposite process, which is stimulated emission, which we can then basically have an external photon would trigger the emission of a photon. And so the falling from level 2 to level 1. And so it would have a different probability from A, which is the spontaneous emission. And so we can define, again, this B coefficient, and it's related to the photon density, the energy density. And again, this is the probability for there to be a transition due to stimulated emission per unit time. And so if this thing changes slowly over the width of the line profile, it'll behave as a delta function. And the probabilities of these things should be more or less equal. Okay, so we can note here that this energy density mu is sometimes used instead of J here, and this just converts this sort of equation by a factor of C divided by 4 pi. But you'll see both. Okay, so if we have thermodynamic equilibrium, all 3 of these processes should balance out. And so we can write this thermodynamic equilibrium equation as follows. So we have the number of atoms which are in the ground state, and this should balance the number that are in the, this is the number that are in the ground state and moving up. And this is the number that are in the excited state moving down. And so if we're in thermodynamic equilibrium, we should have a balance between those 2 processes. And so that's why we factor all of these in. And so we can rewrite this, moving all of the variables so that we're just writing it in terms of this average value of J here. And that ends up giving us a ratio of the number of ground state to excited state in thermodynamic equilibrium. So we can more or less write this as this ratio here, and we can replace these things. Well, we know this ratio of these 2 things is given by this formula here, which is the statistical weights of, more or less, this is kind of related to the quantum mechanical effects, but these are the statistical weights of how you would have a transition, or what are the probabilities between these the ground state and the first excited state actually occurring for a given temperature. And so you have here the energy and the sort of system temperature. The energy is being the energy level between these 2. And so you can rewrite this thing as, well, this you can expand and move out, and then you can reduce this to something which looks like this. And so in effect, it ends up being just related to the line transition as a function of the system temperature. And plugging that back in, we have a relation for this value of J. Okay, so this is simply, to understand how you would populate the different states for a given system energy and for different values of these probabilities, which might differ for hydrogen atom or for helium atom or what have you. Okay, and so in thermodynamic equilibrium, this sort of average intensity should be equal to the Planck black body. And so we can actually substitute that in. And what this allows us to do, this is for, for this to end up being equal for all temperatures. What this means is that this equation has to reduce, or at least allow that this combination, so the statistical weight times the probability of going from 1 to 2 is equal to this statistical weight times the probability of going from 2 to 1. And so this is one Einstein relation. And then another Einstein relation is that the probability of going from 2 to 1 via spontaneous emission is related to the probability of going to 2 to 1 from stimulated emission by this factor here, which comes from, of course, the Planck function. And so these remarkably connect the atomic properties, and there's no reference here at all to the temperature, right? Which is distinct from Kirchhoff's laws, which are a function potentially of the temperature. And so at least for atoms, this holds whether or not the atoms end up being in thermodynamic equilibrium, which is a little bit non-intuitive, but basically this sort of ends up holding for atoms. So these equations are sometimes known as the Einstein coefficient relations, sometimes as detailed balance relations, and effectively they allow you to connect microscopic processes to macroscopic ones, aka emission or absorption on large scale levels. And so it's sort of interesting, one can actually extend this to incorporate Kirchhoff's laws and include non-thermal emission here, in addition to thermal emission, as long as you do the bookkeeping properly. And so the benefit of these sort of relations is that if you can determine one of them, then you can end up determining the other two, right? And they give you useful cross-checks if you know more than one. So this is very useful. And let's see if we can, we'll see more, a little bit more of how to use it later on. So we can then define more generically the absorption and the emission coefficients in relation to these detailed balance coefficients, or the Einstein coefficients. And so let's now think of it, we have our emission, which is distributed over some profile, phi, and this is the absorption. And so we can define a quantity of energy here that is emitted in some volume over some solid angle, over some frequency range, over some interval of time as being this. And now this little j is our emission coefficient, which before we were using epsilon, which is a little mildly confusing, but sorry. It's just to kind of distinguish it. And so if we think about the fact that each atom here is going to contribute a photon, which is going to be distributed over some solid angle 4 pi. So the photon will leave in any direction, right? It's isotropic as far as we know so far. And so what this means is that we will have h nu divided by 4 pi times our line profile times the number density times the probability of this transition times the volume times the solid angle times the frequency times time. And so our emission coefficient here is going to look like this. And so we've gotten rid of these things, but this portion of it is our emission coefficient. And so in order to determine this coefficient, we can think about the total energy absorbed in some portion of time and some volume. And so the total amount that would be absorbed is related to this volume, this time, the energy or the frequency, the number of atoms in the ground state, the probability of absorption, this normalization for pi, and then we integrate over all solid angle, we integrate over all frequencies over the line profile in the radiation field that we have. And so we can do this, and we do these integrals, and we get something which looks like that. Or rather, we don't even need to do this integrals if we just say, okay, we're going to assume this per solid angle and per frequency. So if we end up, this is our emission coefficient, we can think about the same version of this for the absorption. And so we end up, if we think about the volume as being a cylindrical volume of A and ds, the absorption coefficient would end up looking like this. And so it has a very similar form to this. And so as you can see, most of these terms will actually drop out. Now this frequency here is not the total frequency because it's a line profile. And so it has some width to it. And so that's why it isn't here as a nu. So this is excluding any correction for stimulated emission at the moment. So we can now think about the stimulated emission just as we did before, and it should have the opposite sense as the absorption. And so it should be proportional to the intensity. It should only affect photons along the beam. And so it should take place precisely in the same direction, the same frequency, and more or less the same photon state. And these three mean that this is a coherent process. And this allows it to remain as close as possible to the absorption process. And we can write, so we write a negative absorption term, and we include it in the absorption coefficient. And so these two processes together look like this. So you have the absorption, and then you have the negative portion of this, which is the stimulated emission. And then the full absorption coefficient is the difference between these two. Right? It's the effective absorption. And we can then write our transfer equation like we've done before. So we have the differential equation, where we have the intensity, the change in intensity as a function of the path length. This is going to be related to our absorption coefficient times the intensity that we have, right? And so we just plug this in here, and then we have the emission coefficient, which is just going to be the source term. And so we plug that in here. And we can note that we can define a source function again as being related to, well, in essence, it ends up being the number density of level 2 to level 1 times the probability of these transitions. And so if we have our absorption coefficient, we can plug this in again, or we can plug in values for these guys, pull this out. And what we end up having is that this, if we pull out the n here and make these ratios, and 1, we end up having this be 1 minus this ratio of statistical weight times the number density of atoms times the line profile. And so this source function, now that we have this thing here, right? So we have this, we can plug in this, and we also can use the Einstein relations here to get the other values. And we can rewrite this source term in terms of not necessarily the Einstein coefficients, but the statistical weights. And recall that we had this function here, and so that magically appears now here. And this is kind of nice because this now actually looks a little bit like the sort of Planck functionality, and it's just relating the densities and the statistical weights of this population of atoms. And so this is a generalized version of Kirchhoff's law, which applies to line emission in equilibrium situations or in not in equilibrium situations. You could also use a very similar sort of methodology to apply this to other processes, non-thermal processes in general. And so we wouldn't necessarily have, we may have a line width, and this may take different forms. Right, for atomic processes, it is going to be a nice Gaussian line width or something Lorentzian. But other processes could have a slightly different input here. But you could more or less rewrite these in similar ways. Okay, I think that's, oh no, there's two extra slides. So there are a few regimes here where this becomes pretty interesting. One is probably one you've studied before, which is inverted populations. And so if you have a system which is in thermodynamic equilibrium here, this should hold, right? So this is basically that the inverted state here, these should be less than these in thermodynamic equilibrium. And so this implies that you should have this relation. And so even if you push matter out of thermodynamic equilibrium, it's often that this relation holds for what we would call a normal population. But there are some cases where you can invert this population and you invert this particular relation. And what this ends up meaning is that the absorption coefficient becomes negative, or that the stimulated emission starts dominating over the absorption term, right? And so this, if you have the right situation, where you have a very intense radiation field and a certain population, that's in or it keeps getting excited, for instance, then you can sort of induce this stimulated emission. And so the intensity increases along the ray rather than decrease due to this negative absorption. And so this system is what's termed amplified. And this could be a maser, so a microwave amplification, or a laser, a light amplification, optical light amplification, and so forth. In certain situations, when you really push the inversion of the population, so you have most of the atoms sitting in the excited state, this amplification can be very, very large depending on the geometry of the system. And so you can end up having negative optical depths of -100, which imply amplifications of huge, huge factors, right, 10 to the 40 something. And so this doesn't happen very often, but there are certain situations where you have perfect alignment of systems where you're able to get this amplification in nature. Typically, in nature, you don't get amplifications that are this large. But in labs, you can force it that way. Okay, yeah, that's basically, I think, yeah, the first two, where was I seem to be missing a slide because there were two other things here. Where is that? I have to go back. I'm not sure why I'm missing the first two, which are the regimes where you have everything's in a ground state and you have absorption. I need to go back and find those slides. I deleted them accidentally somehow. But let me get back here. Right, so the first one is you have everything is very cool, and you have everything in the ground state, and you have light passing through it, and that system will absorb some fraction of the light at a certain wavelength. Right? And then it will re-emit that light isotropically. And so what happens is the effect is that if you have a continuum source, you'll have an absorption line, which we'll see in the observer at the end of this medium. And then if you look from a different direction and you're not in the line of sight of this emission, right, what you end up seeing is just the emission because it's emitted isotropically. And so you might see a nebula which emits a certain line. And you don't have necessarily a source that's powering it because the source that's powering it is the light's coming from a different direction, which you can't see for whatever reason. It's blocked by a dust cloud or whatever. So that's one situation. Another situation is where you have a plasma and you effectively can, you have something where you have line emission that's heating up this plasma. And so there you wouldn't necessarily see absorption because most things are in the excited state. But you would see some line emission coming from the plasma, which would be a source term as you integrate along the line of sight, along the path. Okay, any questions? I'll try and dig up these slides and put them back in. I'm not sure why they were missing, but they were missing for a while. Okay, if no more questions, then let's move on to chapter 2. And chapter 2 is more or less a review of electromagnetic radiation. And so we'll review Maxwell's equations. And so hopefully these are all very crystal clear in your head, probably a few semesters ago at least. So we can describe electromagnetic radiation as a series of laws, which are Maxwell's equations. And these are, initially were developed as initial laws, and then Maxwell folded them all together. And so the first one is Coulomb's law, which is just that this is, I'm blanking on the name now, the divergence? No. Yeah, I think it's a divergence. So the dot product of the divergence with respect to the electric field, the vector electric field, is proportional to the charge density times some constants, right? Then you have Faraday's law of induction, which is that the divergence, the cross product of the divergence and the electric field will be related to the differential of the magnetic field with time, times some constants. Generally, these things in parentheses are depending on if you're using MKS units or CGS units. Then we have Gilbert or Gauss's law, which is there are no magnetic monopoles, and so the divergence, the dot product of the divergence in the magnetic field should be equal to 0. And then you have Ampere's law, which is that the cross product of the divergence of the magnetic field should be proportional to the derivative of the electric field and this current density. Right, so it's the time. This is the current density, or sorry, the charge density divided by time. Okay, so all of these are related through what we call an equation of continuity, and so this relates. So the change in the charge density with time is more or less related to the dot product of the divergence of the current density, if you move this on the other side, or that this combination is equal to 0, that they balance out, hence the continuity. Okay, so these are our 4 laws coupled by this continuity equation. And if we think about an electromagnetic wave, which is in a vacuum, then these equations simplify greatly, right? Because the charge density is 0, and therefore by the continuity equation, the current density is 0. And so, at least in Gaussian units, these equations simplify to the following. And so the dot product with the electromagnetic field is 0, the dot product with the magnetic field is 0, and the cross product of these is equal to the time derivative of the other one. So, and we have some symmetry here. And so based on these, you can show in a page of math or so that these things should be equivalent to, or you can at least, a form of solving these is based on the vacuum equations. So you have the double time derivative of the energy minus the, I'm blanking on the word for this now. I haven't studied Maxwell's laws in a couple of years. This is, I can't remember. It'll come back to me at some point. If one of you knows it, please chime but the square of the divergence times the electric field. Yeah, someone's searching it. Thanks. And then vice versa. So these allow you to solve for the magnetic field and the electric field. And so these equations are known as homogeneous wave equations. And what comes out of that, a solution of this, is that these two things must be perpendicular to each other. And you can solve them via Fourier transforms by applying Fourier transforms to this. Okay, so this the solution is a wave equation where you have the electric field and magnetic field perpendicular and possibly rotating around as they travel through time. So the solutions look something like this. You have the electric field as a function of position, and time has some amplitude, some unit vector, A1 and A2, and then a complex portion, right? Which is related to this, there's this wave vector here and some frequency, or how it is oscillating. And likewise, you can define the magnetic field similarly. And so these equations where you have this wave vector is defined as 2 pi over the wavelength, or 2 pi frequency divided by c. And this also equals this sort of overall frequency divided by c. And so these are related. But this thing is, with respect to time, and then this actually can be expanded into the 3 dimensions. And so if the solution of these wave equations here is you have a plane wave traveling in some direction k. And so the amplitudes can be related to each other by these equations. And so what this also suggests, if these are related and these are related, you can substitute them out and you end up having this relation here. And of course, these things should be equal. So this should be 1. And so this frequency is related to the wavelength. And thus, the frequency and the wavelength are equal to the speed of light, c is constant. And also these amplitudes must be equal. So all that falls out of this simple electromagnetic wave solution, right? This is all for a vacuum. And so we could generate similar results for a medium that is not a vacuum. And so generally what happens here is that within these wave equations and the wave number, this frequency, they become frequency dependent. And so over very small frequencies, you can get away with something very similar, just with an extra factor here. Okay, so using this sort of terminology, we have this wave going through space, and it has an electric field, it has a magnetic field. And so we can calculate the equivalent force that it would have. And so well, for sort of standard charges, we can think of this force as follows. So we have, for any sort of charge, we're going to have a force equal to its electric field. And then also, if it's moving, we'll have a force related to its velocity and the magnetic field. And so what we're going to eventually do is think about, we have a charge and we have an incident photon, and there's going to be an interaction of those. Or we also can think of the fact that this charge, if it's moving and accelerating, we will have a change in these, which can effectively generate a ray of light. And so we'll come to that in a second, but we're sort of setting up some of the parameters here. So we have a charge, and this charge is at some point r in space. It has some velocity, and so the Lorentz force from this is this combination here. And so we can think of this, we can quantify a rate of work done by the fields on the particle. And so the velocity times this force is will be equal to the charge times the velocity times the field. So we just substitute this in here for this, and we've reconfigured these a little bit, but it's the dot product of the velocity with respect to the electric field vectors. And here, this portion of it, when we do the dot product of this, the dot product of this cross product should be 0 by definition. And so we can then use this version of the rate of work, and we can also think of a force from the actual acceleration versus, for this mass. So for non-relativistic particles, we could actually relate these two forces. And so if we did that, more or less we have this is the work done, sorry, not relate the forces, relate the energies. So this is the work done by the fields on the particle, and then this would be the energy of the particle, right, is the time derivative of the force. And so we can sort of relate these two. Okay. And so we can generalize this to some sort of arbitrary force density is related to the charge density times the electric field and the current density cross product with the magnetic field. And here, this charge density is the summation of all charges in some volume. And the current density is the charge times the velocity in some volume. And then normalized by that volume, right? Or divided by that volume. So we can then sort of reconfigure this in terms of the densities, the charge density and the current density. And so going back, and we can quantify the work done in the same way. And so this work done is going to be the summation of these with respect to the electric field. And this is simply that. And so we have this dot product should be equivalent to the time derivative of all of the mechanical energy within this volume, which we can denote as U mechanical. Right? But that's the charge density. Now, or I guess no, not the charge. This is the energy density. Yeah. Okay. Is everyone with me so far? I'll take your silence as yes. Okay. So basically what happens is that the electromagnetic field that's in this area and the particles are doing work on each other. And so if we calculate the total energy density that exists, that energy density is going to be the sum, or I guess the sum of the squares of the electric field and the magnetic field divided by pi here, just to get the sort of full energy density. And we can calculate some flow of energy through some area. And this flow is going to be given by Poynting's theorem. So the movement of, or change in energy there is just going to be the time derivative of this energy density. And this thing is going to be related to this charge density cross product with the electric field and the Poynting vector here. And this is the divergence cross product with the Poynting vector. And this comes from Poynting's theorem. So this change in energy density is going to be a result of the I guess the work done on the particles by the electric field and the work of the particles on the electric field. Have I said that right? And so this change in energy density at some position in space equals the mechanical work done on the matter, and then it's going to equal some change in the actual electric field, which is the Poynting vector. And so this is the divergence of this Poynting vector, or and the Poynting vector is just the cross product of these two terms. Oh, and all of this is mostly just to have energy balance, right? So the units of this Poynting vector are a flux, right? And hence this is the flow of energy through some area per time. And so we can also think about this in terms of we integrate over the volume elements here. So we integrate this over some volume, we'll integrate this over some volume, and we would integrate this over some area. And then these should potentially be equal. Okay, so another facet of light, and we'll come back to this in a second. We'll be using this frequently for the next couple of weeks. Another facet of light is its polarization. And so we have, we have our equation here for the electric field. And if we think about it in 2 dimensions, right, so we have a propagation dimension, and then generally speaking, the electric field is perpendicular to the propagation direction, and it's perpendicular to the magnetic field. And so you have, they're all always orthogonal to each other. And so if you have some state of this field, you, depending on what axes you choose, you arbitrarily will have some portion which is in the x-axis, some portion which is in the y-axis, and the propagation direction is z, for instance. And so you can divide this into some unit vector in the x direction, some unit vector in the y direction, and amplitudes in each. Right? And these will be equal to the entire amplitude and some unit vector, which is a combination of these two. And here we don't have the K term in here. So we can also think about these, this complex vector. We can put complex amplitudes here and phase shifts. And so we could think about this thing moving as a function of time. And so this would be the phase, how fast it moves with a function of time. And so we could have a phase shift here. And so we could rewrite the portions of E in terms of the electric field in the x direction, the electric field in the y direction, as portions of this phase shift. And so we could rewrite them as this, and it's noting that this exponential, this complex exponential here could be divided into a real and a complex part. Right? Remembering back to your days of calculus. So we then can use these to define what we would term as polarizations, which are in what sense the waves or I guess the fields are moving with respect to each other. And so you could have something which is linearly polarized, something which is circularly polarized, or something which is elliptically polarized. And this is just how fast it's changing in each of these components. All right, and move this over here. So if we talk about, now we can sort of define this. We have a question, sorry. Laplacian, oh, thanks for letting us know. I know I'm late to see your chat, but thanks. Okay, so we can define this sort of situation here. And in general, we have some polarization, some vector, which is sweeping out some form which looks like this. And this is the most generic form, which is elliptical. And so in this case, we have the electric field, which is changing in the y and the x directions as a function of time, which goes something like that. And so we can define angles here. And so we can, the sense of this is that you have either right-handed or left-handed polarization, depending on the sense of this angle theta. And so this radiation will be said to be elliptically polarized if these vectors are not the same, right? And it will be circularly polarized if those vectors are the same. And we can break down these phases into the following. So we can have a sort of normalized amplitude and then sort of portions that map out this phase space here. And this will vary as a function of time. And so one can define correspondences between these components here and a sort of component of secondary angle. And so defining this cosine angle as this combination here plus a different normalization and vice versa. So you can sort of have a combination of these. And in here, this is effectively unit vector 1 or unit vector 2. They're replacing the x and y. So one can solve these, and generally speaking, this overall amplitude is going to be the sum of these two, the sum of the squares of these twos. You can also define something, another, what we call the Stokes parameter. So this is the overall amplitude. So that would be the overall flux of the radiation. And then you can solve, or you can define other quantities, which is Q, which is this difference, which is going to give you the, more or less the ellipticity, it should give you the ellipticity of this, how different this is from this. And then you have U and V, which are more complex sort of parameters, but they give you a sense of what the polarization is doing. I'll give a couple examples here. So we can turn these equations around and define them in terms of these quantities here. And so the intensity will essentially this normalization, the amplitude factor is equal to the square root of the intensity. This factor beta, this angle is related to the V divided by I Stokes parameters. This angle chi is related to the U divided by Q parameters, and I squared should equal the sum of all of these things. And so a couple of sort of extreme examples give you certain situations of polarization. So it's always the case that I is non-negative because it's the flux, right? It's proportional to the total energy flux or the intensity of the wave or waves. V is the circularity parameter. And so if V is equal to 0, then the linear, basically this is linear polarized light. And what this means is the axis ratios are equal. I think, let's see, is that exactly right? Yeah, I kind of want to say, I may have gotten this wrong. Yeah, so basically the V ends up being the circularity. And so if V is equal to 0, it should be linear polarized. Q and U depend on, are mapped to each other, and they're the orientation of the ellipticity. And so if Q and U are equal to 0, there's circular polarization. If they're not equal to 0, then it's linear polarization. And so generally speaking, we never really have monochromatic waves. We always have quasi-monochromatic waves. And so there are superposition of many components. And so it's very rare that you will get fully polarized light from a series of waves. And so generally we talk about polarization as being fractional. And so we can define the degree of polarization as the amount of the intensity which is polarized divided by the total intensity of the light. And so the fraction which is polarized is the square of these, typically it's the square root of these divided by this intensity. And so once you square this, you get rid of the sort of polarization, but the square root of this still in some sense has this polarization, even though it's not quite the same. But roughly speaking, this will give you the degree of polarization you can possibly have. Okay, this is just some basics. We won't go over this too much, but just to give you, when people talk about polarization, and we will talk a little bit about polarization when we come back to synchrotron radiation, because that'll be the first case where we get strongly polarized light.
Here,
Okay.
I have a question about the Stokes parameters.
Yeah.
Well, you mentioned that Q and U are depending on each other and they are related to the orientation or the ellipse. So it's possible to measure Q or U independently, or only we can measure the relationship between both?
No, you can, yeah, I guess I would say once you have one, you know the other. So, I mean, they're tied together in that sense. So you wouldn't necessarily have sufficient information to measure them separately, but you don't need sufficient information to measure them separately.
Okay.
Yeah, my only doubt here is I have a doubt about Q, if I've swapped Q and V. I feel like I have swapped it. I need to check it. And probably checked it like 3 times in the last years, and I always come back and say, oh, okay, it's finally right. But every time I come to it again fresh, I'm like, doesn't quite make sense, because I think this should give you the ellipticity. And then these are definitely, well, these, I guess, okay. No, maybe not. Yeah, okay, I see why. Yeah, so this and this are very, very strong. I mean, these are effectively similar, except for this cosine versus sine, and depend on this chi parameter, which is here, which is the ellipticity. Whereas V only depends on this beta, which is this one angle. So yeah, okay, so this makes more sense then. Even though these actually look more alike. And this is simple. Okay, good, I convinced myself. All right, any other questions? No. Okay, so now we're going to move into the trickier thing, the maybe exciting thing. Yeah.
I have a question, but it's from a past slide.
Which one?
Yeah, one more. No, in the other direction. Hey, okay. Sorry. In the energy density equation, the factor 8p, why? It's an example, or?
Which one? This one?
No, when you, in the first, when you say, assuming we have some energy density equals to E squared plus B squared divided by 8p.
Right. So what we're doing, we take some random value, and we have the charge density and we have the field densities, right? And so the field densities, the energy contained in those is going to be related to the square of the electric field, the square of the magnetic field, and then just normalizing. That's all the 8 pi is. It's just it's a normalization factor.
Okay.
Yeah, well, basically it's 4 pi, right? And then a factor of 2 to split between these two things.
Ah, okay, thank you.
Yeah. Okay. All right. So we have that set up where we kind of related the electric field and the charge density, or like the electric field density, or the magnetic field density, the field densities, and the charge density. And now we want to consider the situation where we have some charge which moves, and actually it's going to accelerate. We want to quantify that, what happens in that case. And so we'll revisit this situation of a charge, right? And the charge is moving now with a trajectory in some vector r. And so this is just some normalization and with respect to time. And it's moving with a velocity v. And so we can define this charge, we can confine it to a very, very small space, and we can quantify it as having a charge density, which is related to the charge, related to velocity, and some delta function, which is locating it in space between r and r naught. So between some time, it will move, and that's where it's located. And so that gives us a charge density or a current density. Right? And likewise, we can do the charge density, which is just the delta function times the charge. So just a simple way of expressing how we would localize a charge that's moving, right? And if we integrate over the delta function, we should get back the charge, we should get back the current, which is just QV. And so we can now calculate the potential, the amount of energy that is changing here, the amount of work that is being done by this certain situation. And so this particular potential that we're going to calculate is called the retarded potential. And this is because there's some delay in the propagation of the field, which we can actually turn into some change in the potential. And so this is, as I said, this is the delayed electromagnetic potentials, which are the work for an electromagnetic field which is generated by a time varying current and a time varying charge distribution. And so how that propagates out, how the field propagates out. So we can define our charge potential, right, which is going to be, now in terms of this, we have it as over some trajectory r and some time t. We have the charge density, and we also have, we're trying to locate it, and so we're locating it in time and in position. And this thing is normalized over the range of space that we're looking at. We're going to integrate this over time. We're going to integrate this over volume. And this, in theory, should give us the amount of work being done here. And so we can move, if we do this integral with respect to the volume, we pull this out, and this just gives us our charge. And so what we're left with is this nasty little thing, which is the delta function. And we can kind of integrate it over the volume and let it pass through there, assuming that this isn't changing, but we do need to do the integral over time. And so that means integrating this delta, t minus t, and factoring in this difference in position. This thing actually is the negative portion of a Green's function. And so we can use that as a substitution for this particular integral. And so the situation we have physically, let's say we have some volume, and so we have some charge, right? So we have some, let's say it's an ionized field for some reason. And so we have some charge here. And we have a movement here of, we're going to calculate the change in field over this distance r and this time t. And so we can relate this situation as this whole thing will be a distance r prime, and then this thing here will roughly be r minus r prime, roughly speaking. And in general, this distance should be larger than this distance. Okay, so that's the sort of basic physical situation. And so we can introduce a variable substitution. So we can define this big R as being this combination, this difference here. And so this allows us to simplify this equation a little bit, at least in looking at it. And so we can rewrite it as this. And we can do a similar thing for the current density. And so the current density, the only difference is the velocity, right? So the velocity times the charge. And so the velocity has a time component, and so it is retained inside this integral. And so after about a page or two of math, which I will not subject you to, but this is done in very quick terms, in Ricci enlightenment, you can solve this by doing this integral, and you come away with a charge potential and a current potential, which are related to this charge, related to this 1 over r, and then everything is kind of encapsulated in this kappa term. And this kappa term is, well, if the speeds are very, very low, then nothing really changes. This thing becomes 1, and you return kind of what you expect. If this thing is very, very fast, the charge is moving, say, relativistically, then what happens is you have an extra term here. And that term is related to the velocity and related to the unit vector, which way this sort of charge is oriented, or the net charge. And this is sort of a minus factor. And so what this does, as you can see, is that if this is non-zero, this is less than 1. And so this is less than 1. And so this is larger. And this is larger. And so if something is moving relativistically for some reason, it seems to do more work. And we'll see exactly kind of what that means in a little bit. At this moment, things are still probably a little bit unclear. I guarantee you, this is sort of a very simplified situation, just to kind of walk you through how we can sort of use this shift to calculate things. And so basically what happens is that this quantity here is sort of related to what we call a retarded time. And so what happens is the charge is moving, the overall charge is moving, and there's some delay as the field is propagating out. And that delay depends on how fast it's moving, because the fields are propagating out very, very fast, not necessarily instantaneously. And so as you move faster and faster, there's the possibility that there's a point in space where we think that we're seeing the field from a point that was, where the say it's an electron, was over here. But by the time we're measuring that, the electrons move and the field has changed, but we don't know that yet. And so that delay in us receiving the information about the charge moving is this time. And that's what we call this retarded time, this delay time. And this delay time ends up having a 1/r behavior, which is related to this r here, or this difference distance here. Okay, questions so far? None, you're still taking it all in. Okay, fine. It takes a couple of reads through to kind of see everything, I would think. Okay, so we can think about this so this is actually from Longair. So there's another chapter, which I think I provided. And I think this might be a little bit clearer in terms of how things are done. So Maxwell's equations are giving us a classical version of electromagnetic radiation. And we think about, in the sense, if you have an accelerating electrical charge, what ends up happening is that you generate radiation from it. And so either that's accelerating, it's slowing down, or accelerating, it's speeding up. And so it's possible here to derive an intensity and an angular distribution of the radiation that would come from a point charge. And this will give some insight on this sort of more global situation. If we think about it in terms of a single particle, right? So we have a point charge, an electron, and it's subject to an arbitrary acceleration. And that arbitrary acceleration is a change in velocity with change in time, right? And this is via Maxwell's equations, and we would include the retarded potentials that we just had calculated. And so this math here is kind of doesn't give you a very good insight into this. And so this is one of the, if we derive it in a simpler way, it's not exactly correct, but it gives you more intuition about this. So let's say we have this particle that's at rest, and we have Coulomb's law here, right? So it has electric fields. The electric fields radiate out radially. And so the electric field is just a radial field. And so now let's push this charge a little bit, right? So we're taking it from rest, and we're accelerating it by some velocity. And this velocity is less than the speed of light, much less than the speed of light. And so at some time later, we're going to have a perpendicular component of the electric field. So we have our radial component, and we have our perpendicular component. And this ratio here is going to be related to our push in one direction, the time, and then the angle with which we're observing that. And so if we're observing it along the push, we're going to see, so if this is 0, we're going to see a maximal change in the electric field. It's perpendicular. If we're observing at 90 degrees, we're not going to see any change because the push is in this direction and the field isn't really going to change. Perpendicular is. If I have my angles right, maybe I have my angles wrong. I have a picture in a second. Right, so this is the angle. Actually, this should be, if it's 90, this is 1. If it's 0, this is 0. So I think I had them wrong. This is the angle between the acceleration vector and the line of sight. Okay. Yeah. Yeah, let me show the picture. I think that'll be easier. Okay. Yeah, I had it wrong in my head. So we have this situation here, and this is a little bit fuzzy, but we have a charge. It's pushed in this direction. And initially we had the radial field with these lines here. The dotted line is the original, right? And then if we move it, this is the new one. And at some point, out here, it's a you see a change. So the propagation of this field change is delayed, right? This retarded time. And so this is the angle phi, I'm sorry, theta. And what we're doing is actually looking for the electric charge in the perpendicular direction. So here, this is moving, and so the radial field is the same. And so there's no change. So so then at 0, this is 0, there's no change here. Or this perpendicular portion is 0, right? At 90 degrees, this is maximized. That's what we wanted to say. And so you can see that here. So this perpendicular component here, you see this change, right? Or it's this perpendicular component. This. And so this is sort of maximized out here at 90 degrees. But this is the change that we're seeing. And so for this to propagate out, let's say it propagates out and we can define a distance which, if it's light propagating out, it's going to be related to c times t. Right, so that'll give us some radius. So if we assume that this field propagates out at the speed of light, then we will have some echo before we're able to actually see it, or some delay. And so what this ends up looking like is something like this. So in this direction, the field doesn't look like it changes. In this direction, we actually see it shift. Right, so it's this perpendicular to the direction of acceleration. Okay, so we have Coulomb's law, right, which is that the electric field is changing as well, it's related to the charge and the square of the radius. So as you go out, it drops off as an inverse square law, right? And we can calculate the perpendicular change in the electric field as this component here. So this is actually just the ER. So in the other sense, it was just down here. So what we've done is multiplied it over here. And this is this change, this acceleration. And then we have a radial term and an angular term, and divided by c. Basically, we're substituting in here that this field is propagating out at the speed of light. So we're substituting in t equals r divided by c from this. And so if we evaluate these things, this perpendicular change in the field is related to the charge. It's related to the acceleration. It's related to our angle with respect to the movement of the charge, and the speed of light squared, and r. And so what's interesting is that this field is changing as 1 over r squared. This field is changing as 1 over r. And so this field falls much, much faster than this field. At large distances, this field ends up dominating, which is interesting. Right, so it's very, very close, this thing that dominates. At very, very far away, this thing dominates. Modulo whatever this value is here, and modulo the angle, right? And so if we have a larger acceleration, we're going to have a larger field. And if we take the ratio of these things, right, move this back over here, and then move this r here, we actually have an r up here now. And so the change in this is a function of r and gets larger as a function of r. Right, if that makes it, if that helps you envision it. Okay, so this equation is really only valid when we have a very small acceleration, but it's valid for any small acceleration, not only maybe a sinusoidal one, if something is moving around. And so the delay time is dropping out of here, and we have a transverse field which instantaneously reflects the applied acceleration. And so if we had a sinusoidal acceleration, what would happen here is that we'd have a sinusoidal variation in this perpendicular field. And as I mentioned, this perpendicular field goes r to the minus 1, not r to the minus 2. And so generally speaking, very, very far away from the field, all you end up seeing is this perpendicular field from the observer's point of view. So what does that actually mean? And so we have visible acceleration perpendicular to the line of sight will contribute to an electric field that's radiated out. And so this sort of invisible component of the acceleration, which is parallel to the line of sight, doesn't radiate. And so we can now calculate how much power comes in any direction from this situation, right? So we can take the Poynting flux, and so in a vacuum, the Poynting flux is simply the power per unit area. And I should probably stop here soon. I'm running over time. And let me just finish my thought here. So you have your Poynting flux, it's equivalent to the electric field cross product with the magnetic field. These are both vectors. And so we can write this as at least the absolute value of this thing. If these are equal for an electromagnetic radiation, we would write it as this, right? Simply from these are for electromagnetic radiation, these are perpendicular. And so you get E squared, B squared, and you have two of those, so you should be able to divide this out. Actually, is that right? No, sorry, you have E times B because they're perpendicular, so you end up E and B are equal, so you can have E squared or B squared. So you get this out, you can plug in the perpendicular component of the electric field, which you do here, you square it, and you get some Poynting flux, which is non-negative, which is related to the angle here, square the angle, related to the acceleration, related to the charge, and related to the distance. And so this is what this thing looks like. So you have some component that's coming out with some solid angle from a charge which is accelerating in this direction. And so the field is maximized perpendicular and is lower as you go to smaller theta, right? And so the field looks kind of like this, and in all directions. And so if you had some geometry which looks like that, the field coming out would look something like this. Where this is just telling you the amplitude of E perpendicular. Right? So E perpendicular very close would be very small, and perpendicular would be very large. And so it changes something like that. Okay, that's more or less all I wanted to say now. This is what we call Larmor radiation. And so the derivation we just did was the Larmor derivation. And so we can use that to come back and sort of try and understand this a little bit better. All right, so we'll do that in the next class. Okay, any questions?
This is only valid for the vacuum because, or this also valid for a medium?
I'm not sure I quite understand what your question is. So it's only valid for an electron, or it's valid for multiple electrons, or?
No, I mean, because I was thinking about the delay, and the delay here is only because of the movement of the particles along the time. But also, if, for example, we include a medium, the velocity of the light is changing because of the medium. So in that case, for example, if we have some material, this Larmor equation applies also, or it would be different, or?
Well, let's separate the situations. I think we may be getting ahead of ourselves, but the first thing is just we have a simple case of an electron, and then it radiates some energy away in the form of its electric field, which we will eventually end up calling light. So this is how light is generated from accelerating particles. Now, what you're talking about is some medium. Is that medium affecting the light that's being generated out, or is it contributing to it? I'm not exactly sure which you're asking about. If you're asking about the former, right, we'll get to what's happening after it's radiated out in a little bit, right? But we're just going to talk about the sort of microscopic portion of this for the moment, and then we'll deal with ensembles a little bit later. And because there will be an absorption term related, if there are multiple electrons, you'll have some that will be able to absorb the radiation that's emitted from others. And I think that's what you're getting at, but I'm not sure.
Okay, thank you.
If I didn't answer your question, let me know. I wasn't sure about what you meant by the medium. No? Okay. Okay, we'll think about it, and you can ask questions during office hours on Friday or next Monday. Yeah.
I also have
Any
a
other
question
things?
related
Sí,
to
sí.
the office hour, because I think that the office hour is overlapping with the Frontera seminar.
Shouldn't be. It should be right after Fronteras.
Yes?
It should be 12 p.m.
Ah, okay, yes.
Do I have it wrong somehow? What did I say? Did I say mod 2 or something, or mod 3?
No, I checked the web page a few minutes ago, and it's at 12.
Okay.
12?
The office hours. Yes.
Okay.
Okay.
Yeah.
Professor, in order to send the homework, we have to send it like directly to your mail or via Canvas, or?
Either way is fine.
Okay.
Yeah. Yeah, if you send it to my UC account or to astrobook.cl, they're equal. Eventually, it all goes to my Gmail anyway. So whatever email address you use, I will get it. Typically, what I do is just download it to a Dropbox and give it to the Aidante, and they will grade it. Okay. ¿Algo más? Anything else? Okay. Good. Well, have a good rest of your Wednesday. See you in Astro PH next tomorrow. Yeah, I did. Also, I didn't know that you guys don't have astrobook.cl email yet. So this is
No.
yeah. Hopefully that gets resolved soon. But if it doesn't, please be vocal and say something. Probably during Astro PH. If it's not solved on Friday, for instance, we should try and get it done quickly. Okay. Okay. Ciao todos.
Ciao.
Ciao.